Imagine stepping outside. It's a bit too warm, and your shirt just opens up these tiny vents to cool you down, all by itself.
Or maybe you're handling something really, really fragile, like a piece of ancient pottery, and your glove just knows to perfectly adjust its grip pressure.
It sounds like something straight out of a Marvel movie, right?
It really does. But
Yeah.
this is here right now. And the most fascinating part is that this tech, this ability for fabric to literally change its shape and stiffness, is all controlled by magnets.
Exactly. So today we are doing a deep dive into a really groundbreaking research paper published in the journal Nature. It's from Junghong Pu, Xiaoming Tao, and their colleagues over at the Hong Kong Polytechnic University.
And their creation has let's say, a very scientific name.
It's a mouthful.
It is. It's called vector stimuli responsive magnetorheological fibrous materials. But our mission today is to break that down because inside that dense phrase is a huge leap forward for technology.
Okay, so let's start with the problem they were trying to solve. Smart textiles aren't totally new, but they've always had a pretty big limitation.
A huge one. Historically, they only reacted to what we call scalar stimuli. So think of scalar as just a simple number. Temperature goes up, humidity changes. It's a single input.
And the reaction was basically on or off.
Exactly. It was a binary switch. There was no finesse, no directional control. You couldn't tell the fabric, okay, I need you to bend exactly 5 degrees to the left. It was just a generic response.
Then all or nothing kind of deal.
Precisely. So this new technology introduces what the researchers call vector control. And a vector has both magnitude and direction.
Okay, so it's not just how strong the effect is, but which way it's pointing.
Yes, the direction and the strength of an external magnetic field now dictate exactly what the material does. We're going from simple switches to fully programmable directional manipulation.
So we're talking about fabrics that can bend, that can stiffen, that can even change their texture, all on command, just by using a magnetic field.
It's like having these tiny little microscopic machines woven right into the thread itself.
Oh.
And to do that, they first had to perfect the thread.
Right, so let's get into the main component here, these magnetorheological or MR materials.
So MR materials are this really cool class of smart materials. The name kind of gives it away. Magneto for magnet.
And rheological.
Rheological just means it changes its flow or mechanical properties.
Okay.
So it changes how stiff it is in response to a magnet.
And how does that work? What's actually happening inside the material?
Well, you have these tiny magnetic particles suspended in a flexible material. When you apply a magnetic field, the particles suddenly attract each other. They line up and form these little chains, these microscopic chain-like structures.
Almost like a temporary skeleton inside the fabric.
That's a great way to think about it. And that internal skeleton makes the whole material instantly stiffer. So for this, the researchers used low-density polyethylene, or LDPE, as the flexible polymer.
Okay, that's a pretty common flexible plastic.
Exactly. It's easy to work with for making textiles. And for the active ingredient, the magnetic bits, they use something called carbonyl iron particles, or CIPs.
Now, I'm guessing you can't just, sprinkle some iron filings in there and call it a day. They needed the perfect recipe.
They really did. They tested a bunch of combinations and found the sweet spot was a composite that contained a whopping 70 weight% CIPs.
70%. So most of the fiber's weight is actually the magnetic particle. That sounds really dense.
It is, and that was the key. They needed that high filler content to get a really strong reaction to the magnet while still keeping it flexible enough to be made into a thread.
Did they run into problems with it being too dense? Like, did it get brittle?
That's a great question, and yeah, that was the engineering challenge. They even tried an 80% mix, but it became too solid, too unstable for production. 70% was that perfect balance.
And this brings us to what I think is a huge part of this story. They figured out how to make it at scale. This isn't just a tiny piece made in a lab.
Oh, absolutely. The team was focused on this being commercially viable from the start. They used standard industrial methods, melt spinning and high-speed drawing, to produce these MR fibers continuously.
And the fibers themselves are incredibly thin, right?
Only 57 micrometers in diameter. I mean, for perspective, a human hair is about 100 micrometers. So this smart thread is thinner than a hair.
And they can make a lot of it fast.
That's the game changer. They clocked a production speed of about 2 kilometers per hour.
2 kilometers an hour.
Yeah. Previous smart fibers were often made, a few centimeters at a time. This is industrial scale. This is something you can actually use to make clothes.
And then from there, they twist 7 of these fibers together to make a yarn.
A very durable yarn. It could withstand 10,000 repeated bending cycles. You could even tie it in a knot and it wouldn't break or lose its function. It's tough stuff.
Okay, so we have this amazing scalable smart thread. Let's get to the vector control part, the part that really sets this apart. Bending versus stiffening.
Right, this is the magic trick, the ability to pick the function just by changing the direction of the magnetic field. So if you apply a field that's non-parallel to the yarn,
So like sideways to it.
exactly, it creates a magnetic torque, a twisting force, and that forces the yarn to physically bend and try to line up with the field. It becomes a tiny, controllable muscle.
And a strong muscle at that.
Yeah.
This is the wow fact for me.
Oh, yeah. They tested a tiny little piece of this yarn, just 10 millimeters long. It was able to lift 185 times its own body weight.
185 times. That's like
Yes.
me trying to lift a car with my pinky. It's an incredible amount of force from a flexible thread.
It really is. Now, what happens if you change the field's direction?
You switch modes.
You switch modes. If you apply a magnetic field that's vertical, so it's running parallel along the yarn, you get the stiffening effect.
Mhm.
The yarn stops being a muscle and becomes like a temporary bone.
So instead of moving, it just locks in place.
Right. That parallel field makes all those little iron particles inside attract each other as strongly as possible. It creates intense internal friction, and the yarn's rigidity just skyrockets
By how much?
by about 30 times. The bending rigidity increased by a factor of 30. It goes from feeling like a normal, soft piece of yarn to something extremely stiff.
A 30-fold change. That's like instantly switching from a silk scarf to a steel rod.
It's a huge range of tunability. And crucially, it happens in a very safe magnetic field under 300 millitesla, which is important for anything you're going to wear against your skin.
That makes sense. Okay, so now we have this revolutionary yarn. How do they actually turn it into fabric that does something useful?
They made two main types of fabric. One was a traditional woven fabric, like you'd find in a shirt. But the other, and this is where it gets really interesting, is a cut pile fabric.
Cut pile. Like a carpet, where the fibers stand up.
Exactly like that. Tiny, programmable carpet fibers. And they use these to build some incredible prototypes.
Let's start with application one. The active ventilation fabric. This is for sportswear, right?
Absolutely. They built a tiny linear actuator into a piece of woven fabric. And when they pulsed an electromagnet, it made the actuator move, opening and closing little slits in the material.
So the fabric is literally breathing.
It's creating a fluttering motion that pumps air through, actively ventilating you. And they showed they could increase the fabric's breathability, its water vapor permeability, from about 34 up to 58.5 grams per square meter per hour.
Just by changing the frequency of the magnet.
Just by changing the frequency, your shirt could literally adjust its own breathability in real time.
Okay, now for the robotics application. The conformable gripper. This uses that carpet-like fabric, right?
Yes, the cut pile fabric, those little vertical fibers. By applying the magnetic field, they could instantly change how much the surface resists being squished.
So they can make the gripper surface go from soft to firm.
Right. They could tune the compression modulus up to 22.5 kilopascals. This lets the gripper be incredibly gentle. Instead of a hard, rigid claw, it can conform to the shape of something fragile. They showed it picking up soft tofu, a live worm.
Even a potato chip.
Even a potato chip without crushing it. It distributes the force perfectly. It's the ultimate soft-touch robotic hand.
And finally, the application that I think is the holy grail for virtual reality. The untethered haptic finger glove.
This one is just so elegant. It combines both types of fabric. The woven MR fabric is used along the finger to provide kinesthetic feedback.
Okay, so that's the feeling of resistance, like when you try to close your hand on a virtual object.
Exactly. It stops your finger from moving. And then on the very tip of the finger, they put the cut pile fabric. That provides the tactile feedback.
So that's the feeling of texture, hardness, smoothness.
Precisely. So if you touch a virtual brick wall, the woven fabric locks your finger in place, and the cut pile fabric at the tip stiffens up to make the surface feel hard.
And it actually works. You can feel it.
Oh, yeah. The glove generates up to 150 millinewtons of force on the fingertip, which is well above the human perception threshold of about 10 millinewtons. You can absolutely feel the simulated texture.
And this is so different from the haptic gloves we see today, which are often these bulky things with motors and air pumps.
That's the beauty of it. This MR glove is just fabric. It's lightweight. It's not restrictive. The fabric is the interface. It's a massive leap forward.
So let's wrap this up. This work by Pu, Tao, and their team really provides this incredible framework, blending material science and textile manufacturing to get this unprecedented level of control.
So let's go over the key takeaways from here.
First, vector control is the future. We're officially moving past simple on-off switches and smart textiles. We now have directional, programmable control using safe, external magnetic fields.
Second, the unmatched material performance and scalability. This MR yarn isn't just a lab curiosity. It can be made at 2 kilometers per hour, and it has that phenomenal 30 times stiffness range. That soft to hard duality in one material is unique.
And finally, haptic and adaptive applications are here, and they're lightweight. We saw functional smart clothing like that ventilation fabric and these incredibly sensitive interfaces like the robotic gripper and that haptic glove.
This research really elevates smart textiles. They're not just passive electronics you wear anymore. They're active, programmable materials that can change their shape to interact with the world around you.
Which leaves us with a final thought. If our clothes can now be actively controlled by these external fields, giving us haptic feedback and real-time ventilation, what happens when we integrate this with AI? Will our clothes eventually be able to adapt their physical properties for us, even faster than we realize we need them to?